Welcome back to My Smart Learning. This is a lesson for Year 10s, the guys that are missing my lessons while we're on this lockdown. It's a GCSE lesson, physics lesson, and we're looking at electrical circuits. So there have been a lot of students missing from the last week of term, so I'm going to recap on the things that a lot of students, some of you were at school, some of you weren't, but half the class was missing. So I'm going to recap on any of the information that you've missed as well. So we're looking at VI graphs. So some of this will be a bit of revision for some of you. Some of it is going to be completely brand new. When I set lessons for next week, we're going to start looking at new content that none of you have done before, which is about series circuits and parallel circuits. So VI graphs for circuit components. What are we looking at? Learning objective. How does current behave through various components? Now the components I'm looking at today are fixed resistors, the wire, which you guys have done, the filament bulb, diode, an LDR, which is a light dependent resistor, and the thermistor. Now, as you know, I like to start my lessons with a quick recall PT, progress testing, but I've rephrased it, I'm going to recall them now. The recall quiz, high five. Get them all five right, you get a virtual high five from me. So, number one. Some formulae you should have remembered from your previous lesson. Q equals what? So Q equals something times something. That's a bit of a clue for you there. Q equals, question 2, V equals, what does V equals, depending, this is one that you learned with Ohm's law. Can you remember what V equals? Question 3, E equals, so depending on electrical charge, what does E equal, electrical energy? I'll give you a bit of a clue in that question there. Question 4, what is the unit of resistance? So what is the unit of resistance? And question 5, what is the unit of charge? So pause the video very quickly, have a quick check of your answers, and I'll go through them now. So Q equals, if you can recall, Q equals IT. So what does Q stand for? Q stands for charge. And charge is equal to I, which is current, times T, which is the time, IT. So I told you to remember it as quit. Q equals IT. I standing for current. What's the current measured in? It's measured in amps. And time must be converted into seconds. So if you get any exam questions, the time must be converted into seconds. So if it's 1 minute, it will be 60 seconds, 2 minutes, 120 seconds, and so on. V equals, based on Ohm's law, V equals IR. V equals I times R. So the voltage, or the potential difference, which is the correct word for it, the potential difference, voltage equals the current times the resistance. So again, current is measured in amps, and the resistance, which we'll come on to in a minute, is measured in ohms. E equals, number 3, E equals QV. E equals Q times V. So energy, electrical energy in the circuit, is the Q, which is the charge, times the V, which is the potential difference or voltage. So the units then, question 4, the unit of resistance is ohms. The Greek letter we use is omega, which looks like that sort of horseshoe shape. And the question 5, the unit of charge is coulombs. Coulombs, C-O-U-L-O-M-B-S, coulombs, as a capital C. If you got them all right, that's excellent. You get a virtual high five from me. Now, what did some of you guys miss? So over the last week of term, not term actually, over the last week before we all got shut down, we did the resistance in a wire required practical. And in that circuit, what you have to do is we had a meter rule, and on that meter rule we had a thin piece of wire. Now it's either made from constantan or nichrome. And what we did with the crocodile clip, we connected it on the 0, and then we measured it at different points. So we put the other side of the crocodile clip on 20, 40, 60, 80 and 100. And it was connected in a series circuit. So what we had was we had an ammeter, which is measuring the current, and we just had a battery, well, a cell, just one cell. Remember, just one of them is called a cell. When you have multiple cells, we call it a battery. So we just had one 1.5 volt cell, and we got some excellent results from that. And we connected the voltmeter in parallel across the area along the length of the wire. So what did our results table look like? Our results table looked like that, and we measured it at 20, 40, 60, 80 and 100. And with our voltmeter we measured the potential difference, and that was measured across those two wires where the crocodile clips connected. We had to connect the leads directly into those leads, but the ammeter was just in a loop in series, so we measured the current. To calculate the resistance, if you remember Ohm's law, V equals I times R. So if I want to work out the resistance, it's the voltage divided by the current, and that's what you did. So you did the voltage divided by the current, which you calculated the resistance. And some of the results that we collected from the class, so this was one group's results. This was when we used multiple cells. We got, if you notice, the voltage is increasing, the potential difference is increasing. What's happening to the current? The current is decreasing. And if we divide the voltage by the current, well, what's happening to the resistance? The resistance is increasing. Well, why is that? Why is it that if I have a longer wire, so if I just go back, if I measured it there, to there, to there, to there, to there, why is it when I get a longer piece of wire that you get a higher resistance? Well, we saw that the current decreased. The current decreased because if you've got a longer wire, remember the definition of current, a current is the rate of flow of charge. It's how quickly those electrons, which are carrying a negative charge, are flowing through the conducting material. Here it's the wire. So if the wire is longer, there are more ions or more atoms for the electrons to pass through, therefore it's making it more difficult. So they're going to collide and bump into more of those atoms, and therefore making it more difficult for the current to flow, and therefore you get a higher resistance. So the conclusion for that particular required investigation, the longer the wire, the higher the resistance. It is harder for the current to flow through the wire as it gets longer because it's got further distance to go. So that's quite a straightforward one. If you plotted the graph, this is what it would look like. So if I got the length of the wire, so I got 20, 40, 60, 80, 100, you could go longer, and then you measured the resistance. These are the results based on our results that we got. You got, if we draw a line of best fit, we can see that based on this graph, if we had to mathematically do a conclusion or analysis of this interpretation, the longer the wire, the higher the resistance. Would probably get you 1 mark, but we can see from this is directly proportional because it's going through the zero there. So therefore, we can say it's a directly proportional relationship. Now, the other part of this required practical, we need to go through some components. So the components we looked at, one of them was a fixed resistor. So a fixed resistor is exactly the same as a fixed length of wire. So you'd get the same results for a fixed resistor as well as a piece of wire, a length of wire. So again, we've got an ammeter connected in series to our component. So our component here is the fixed resistor. I'm connecting the voltmeter to measure the potential difference or the voltage across that component, the resistor. It's going in parallel, so it's going across that because I'm trying to measure the energy difference between those 2 points. This little variable resistor there is just so that you can amend the amount of current or the amount of current flowing through this. You could, instead of having a variable resistor, you can just keep adding cells. So instead of having a variable resistor, I could start with 1 cell, 2 cells, 3 cells, 4 cells. If it's a power pack, I could just start from 2 volts, twist it to 4 volts, twist it to 6 volts, 8 volts, 10 volts, 12 volts, something like that. That variable resistor kind of does the same thing for us. It just slides up and down, changing the amount of voltage that this will get. So, what kind of results should we expect? Well, you'd get exactly the same as before, where you get a straight line. Because if I increase the potential difference, the voltage, the current increases because you're giving more electrical push, more energy. So the current flows faster. So you get a directly proportional relationship. So the higher the voltage, the greater the current, but it's directly proportional. It starts from 0 and it keeps going up in a straight line. So if I double the current voltage, I'll double the current. And that was what we did in Ohm's law. Remember, Ohm's law states that the current is directly proportional to the voltage applied, or the potential difference applied, as long as the temperature remains constant. Because the wire must stay the same temperature, the resistor has to stay the same temperature. And we'll come back to that in a second, because we'll look at the filament bulb in a minute or two. So, but why have I got a graph that goes this way as well? Well, this is if I've got the cell or the battery facing one way, I'd get positive results. So this would be a positive number, that would be a positive number. But if I turn the battery around, so it's facing the opposite direction, you don't get a smaller number. It's just purely to do with the direction it's going. So it would turn direction, the current would flow the opposite direction. You'll get a negative reading on your voltmeter and your ammeter. In magnitude size, the actual size will be exactly the same. It's just that it's flowing in the opposite direction. So it's almost like a mirror image of what's going that way. So if I've got the battery this way around, it goes that way. If I've got the battery the other way around, it'll go the other way. But again, it's directly proportional. If I increase the voltage or the potential difference, the current increases by the same amount each time. And that's what directly proportional means. Our next component then is our filament bulb. Okay, we have to call it the filament bulb because there are different bulbs now. You've been studying this for decades about how current behaves through a filament bulb. There are obviously different types of bulbs now, like LED bulbs. But for a filament bulb, this will happen. So exactly the same setup again. It's a series circuit with your bulb. And in that series circuit, I've got an ammeter to measure the current. And I always put my voltmeter in parallel across the component, so I can measure the potential difference between those 2 points, what's happening to the bulb. And again, you can have a variable resistor to change the amount of energy you're receiving from that cell or the battery. An easier way, what we did in our practical in the classroom, we just kept adding extra cells. So we started with one cell, which is 1.5 volts. We added another cell, which made it 3 volts. We added another cell, which made it 4.5 volts. Then we added another cell to make it 6 volts, and we used a 6 volt bulb, and we based it on the results from that. So we couldn't do any more because it would potentially blow the bulb. And the other thing you could do is just use a variable resistor just to control the amount it's getting. So what kind of results do we get? So this is half the class we're missing that last Thursday and the Friday of term. So your results table looks like this. So you just measure the potential difference of the voltage. You write down the current that you get. And you could also calculate the resistance by doing voltage divided by current. Now here's some of the results from some of the groups. So you can see as I increase the voltage, the current is also increasing. But what can I see? It's increasing fairly constantly, but then suddenly it starts to slow down. It starts to level off. It starts to plateau. So that's the observation you should be able to see. And look, the resistance, if I do V divided by I, the resistance also increases. So the wire's getting less current, but the resistance is increasing. Why? Well, what does it look graphically? So here's some more results from a different group, going the opposite way around. But again, you've got the same kind of pattern. It's increasing, and then it starts to level off. So it's the opposite way around. Okay, but again, you can see the resistance is increasing. At first the resistance is low, but then the resistance starts to increase. Well, if I do it again graphically, if I just had this half of the graph, you can see it goes up and then it plateaus. And if I turn the battery round, or the cells round, the voltage round, you get exactly the same pattern. It increases and then it plateaus. It's just a mirror image of that. So you get this S-shaped curve. And you need to memorize the shape of these graphs for your exams. So how do you explain this? How do you explain why is the graph going up in a straight line but then starting to level off? Well, remember in Ohm's law says that the current is directly proportional to the potential difference of the voltage applied as long as the temperature remains constant. Now, is the temperature remaining constant here? This is a bulb, a filament bulb. And what do you know about filament bulbs? If you switch them on, if you put your hand on them, they get hot. So if they're getting hot, something's been happening to the resistance. So as you increase the potential difference, as you give it more and more energy, more and more current starts to flow through them, they start to get hot. And as they get hot, the atoms, they start to vibrate more, the ions in the metal wires inside the filament bulb. And if they're vibrating more, it's making it more difficult for the electrons to pass through. So as I keep increasing the voltage, the potential difference, the current would like to carry on going straight, but it can't, because the atoms are vibrating so fast that the electrons try to go past, but they can't. They're getting inhibited by these moving ions. So it starts to level off, so it can't increase anymore. So that's why you get this shape. The other one that you need to know is your VI graph for a diode. Now, what is a diode? Here's the symbol for a diode. A diode is a component, an electrical component, that only allows current to flow in one direction. So, for instance, here, the current will flow. You'll go through there and through there. But if I turn the diode round, the current wouldn't be able to flow. Or if I turn the battery around on this one, the current wouldn't be able to flow. So a diode only allows current to flow in one direction. So if I got current flowing this way, I'd get a reading on my ammeter and my voltmeter. If I turn the diode round and I switched on my circuit, you'd get nothing there and you'd get nothing there. Okay, you would actually get some voltage because it would show you that there is something trying to get across there, but it's not allowing the current to flow. So what do our results look like? A results table will look like this. You'd measure your potential difference and you'd measure your current. And here's some results from the lesson. So now I had -2 volts, -1. So obviously the battery's the wrong way around, so I've got the opposite direction. You'd get no current at all because it's not allowing, the diode will not allow the current to flow through. At 0, there's obviously nothing. But here's the thing, when I've got 1 volt, I'm still getting nothing. But then suddenly, got 2, 3, 4, I'm starting to get a current. It's going up by the same amount each time. So what does it look like graphically? So again, I've got my current on the y-axis and I've got my potential difference on the x-axis. And this is my negative side. So if I've got my battery the wrong way around and I'm trying to generate a current, I'm getting, there'll be like -2, -1, 0, like on the previous data table. You're getting no current. You are getting a reading on the voltage, but you're getting no current. Nothing is flowing through because the diode only allows current to flow in one direction. But what's happening is after 0, I get 1, well, I still get nothing, but then I get 2, it starts to rise. 3, it starts to rise. 4, it starts to rise. And it starts to behave like a normal, what we call ohmic conductor, just like your fixed resistor or your wire. So it behaves like a normal wire after that. So again, why not there? Because it won't allow the current to flow in that direction. But why doesn't it go straight from here? There's a slight threshold. You need to give it just enough push in the first place. You won't just do it straight away. You have this threshold that you have to reach first. Give it just enough potential difference. And once you go above that threshold, then it will start to behave like a normal ohmic conductor. Okay, so last 2 components that you need to know about. We've got what we call an LDR. So that's your symbol for an LDR. Stands for light dependent resistor. Light dependent resistor. And we've got over here your thermistor. Now what do they do? Well, you can kind of work this out. Light, it depends on the light. Those 2 little arrows represents the light, and the light is going into this component. Now, what does a rectangle symbolize in circuit diagrams? Well, the rectangle represents resistors. So it's a light dependent resistor. And this one is, again, it's a resistor, but this little line with a little dash there represents that it's a thermistor. So it's again a resistor. What's the therm represent? Therm meaning heat. So this resistor will behave differently depending on the heat. This resistor will behave differently depending on the light. Now, where would we see these components? Well, this component, if you notice your street lights outside, when it starts to get dark, the street lights start to come over one by one. Well, is it somebody going around the individual lampposts and start switching them on? You don't see anyone walking around. Or is it somebody in a power station switching them on one by one? No, because if that was the case, if somebody flicked a switch, then all of them will come on instantly at the same time. If you know, next time you notice, when you go around, you'll see they sort of start flickering on one by one because they've got sensors on the top. Now, if you look from, sometimes you've got a lamppost sort of outside your house, you might be in a bedroom that's slightly above or higher than one of them. You should notice there's a little cap on top of the lampposts, and you'll see that there's, in that little cap at the top, there's little components in there, and one of those components is an LDR. It's a light dependent resistor. And when it starts to go dark, it actually recognizes that the resistance changes. It starts to get a greater resistance in them, and therefore the circuit realizes it's getting dark and the lights switch on. So it's a bit of a counterintuitive thing. So if it becomes brighter, the resistance decreases because it's allowing more current to flow through. So that's one place you see an LDR. A thermistor, where would you see a thermistor? Well, a thermistor you find them in the thermostat, because the circuit will either come on or off depending on the particular temperature it's at. So for instance, if it's getting too cold in your house, you might switch on the central heating because it might be on a thermostat. It could be in an incubator where a newborn baby can't control their body temperature, so they need to have something to switch on the fan to cool them down, or to switch on the heating element to warm them up if the temperature's not the right temperature. So how does that work? Same again, it's a bit of a weird one, it's a bit counterintuitive, where as it gets warmer, the resistance decreases. So if the resistance decreases, that means there's more current flowing through it. So if it's getting hotter, there's more current flowing through it, but if you want to switch it off, then you need to tell the circuit, switch me off. So what do they look like graphically? So a light dependent resistor looks like this. So if I have more light, the resistance decreases. So if you had to turn that around and do it as a current graph, so if that was the amount of light, the current would go up, because if there's less resistance, there must be more current flowing through. So the more light, more current. Therefore, less resistance. And for your thermistor, same again, the hotter it gets, the lower the resistance. So again, if it's getting hotter, that means there must be more current flowing through. It'll be the opposite line to this. The current would go the other way, like that, showing you that there's more current going through that circuit. So that's your lesson on VI graphs and the different components. What have we learnt about? We've learnt about the resistance in a wire investigation. The longer the wire, the higher the resistance. We've learnt about how you measure the VI across a fixed resistor and how that looks graphically. You've got a straight line going through the origin, and it's the same thing for a wire. And we looked at the filament bulb, and we looked at the diode. And we've also looked at the last two components here, which is the light dependent resistor and the thermistor. Hopefully you've learnt something today. So if there's anything that doesn't quite make sense, use Show My Homework. There's a lot of you already asking me questions on Show My Homework. You can also ask me through the YouTube channel. But I hope you're all staying safe indoors, even though there's lovely sunshine outside. Remember to stay at home so we don't spread this virus. And hopefully we'll see you all again back at school as soon as possible. If not, catch me here again at My Smart Learning. There'll be more and more videos being posted every day. Hopefully it's been useful and you've learned something. Please go on to watch them, like them, subscribe to the channel, and then share it so more and more of us can do a bit of learning. See you next time. Take care. Bye.